Okay, yeah, so we're back. We're in the middle of chapter 14, sort of, or wherever we are. I would say, we can work on anything here today. 14.1, 14.2, and 14.3. 14.3, we got to switch these double integrals into polar coordinates, so that was some good stuff. Do you have any requests? No? Okay. Well, I can handle all this without requests. Let me see here. So like 13, and 13's kind of easy. Man, maybe I don't want to do 13. In fact, that was your homework. Well, okay. All right. About 11 right here. In 14.3, number 11 is a problem, and it's just a double integral. It's already in polar coordinates. 3r squared sine theta dr d theta. 3r squared sine theta dr d theta. A lot of times they're in x's and y's, and then we have to convert to polar coordinates. That's kind of, we did one example like that the other day, but this one, it's already in polar coordinates. They're just asking me to do it. The bounds are 0 to 6 and 0 to 2 pi. So one of the things I think they're asking is to do the integral. So that's cool. We could work on doing the integral. But the other thing they ask for is, can you describe the region over which we're integrating? So let's talk about that first. The region over which we're integrating is all about these bounds. I've been saying that for a few days, keep saying that. There is a surface here. There's a z equals a function of x's and y's, but not x's and y's. Apparently the x's and y's have been converted to r's and thetas. But there is a function here, z equals this, in r's and thetas, that is some surface, 3D surface. We're integrating under that surface over the region R. So this ain't about the region R. The region R is here, described in the bounds. And let's just talk about that real quick. So R is the variable that goes from 0 to 6, apparently. And if you know your polar coordinates, or you're getting used to your polar coordinates, R is kind of a stick that goes from the origin out. So from 0 to 6 might be something like this, where you hit a radius of 6. 0 to 6, 0 to 6. Here's an R going from 0 to 6, 0 to 6. Now, it does that while theta does 0 to 2 pi. Well, okay then, 0 to 2 pi. I think we just described our region, but it's in polar coordinates, so it takes a little getting used to, but polar coordinates are easy once you're used to them. R goes from 0 to 6. Theta goes from 0 to 2 pi. I believe we're integrating over a circle of radius 6, centered at the origin. That's the region over which we're integrating. There is a 3D surface over here that we're integrating. There it is. I don't know what it looks like. I'm not sure I care. But I just wanted to describe the region over which we're integrating. So that's cool. We can try cranking this out. Step 1 is try to integrate with respect to r. I guess that's not too hard. R cubed. You treat the theta like a constant, so you treat the sine theta like a constant. So you're integrating just with respect to r. R cubed, you divide by 3. Okay, there it is. The sine theta is a constant that sits there. The bounds for r are 0 to 6, so we evaluate. We plug in our 6. Turns out 6 cubed is 216, I think. And then the 0 would be 0. So here I am. The inner integral was done. The inner integral was evaluated. And I'm left with an outer integral from 0 to 2 pi. and it's with respect to theta, and right, there's just one variable left. I integrate with respect to theta. Here we go, integrating a sine theta. I get confused sometimes. Let's see. The derivative of cos is negative sine. So if you're trying to integrate sine, you get negative cos. So this is negative 216 cos theta. That's the answer. And I have to evaluate it from 0 to 2 pi. This could be interesting here. When you plug the 2 pi in there, it's the cosine of 2 pi, which is a 1. But it's multiplied by this negative 216, so we get negative 216. Minus the negative 216 times the cosine of 0. The cosine of 0 is a 1. So the first answer was negative 216 minus the second answer, which is negative 216. But then that ends up being plus 216. This is a 0. That's okay. The answer is 0. It might be fun to think about what that might mean. I mean, I thought the way I talked to you guys, I thought there was a surface up here. And I was finding the volume between the surface and the region in the xy plane. Because it came out to 0, is there anything you want to say?
It's a height of 0.
Right? It doesn't have a height of 0, I don't think. I think it's got some different heights out here. But remember, I said this a few times, we haven't really run into it. Volume below the xy plane, the double integral calls that negative volume. It'll crank out to be negative volume. Volume above the xy plane will be positive volume. Now, what I think happens here is that this function over this region is not over this region. Part of it is over, part of it is under. In fact, exactly half of it is probably over, and exactly half of it is under. And that's why I ended up with a net volume of 0. That's probably what happened here. Whatever this z surface is, it's slicing through the xy plane somehow, but exactly half of this, halfway through this region somehow. You know, maybe this half, or maybe this half, or I'm not sure what half, but that's my, yeah, that's what it's got to be. That there is some volume, but doing a double integral like this, there's some of this volume was above the xy plane, some of it was below the xy plane, and the answer came out to 0. Right? Not only just some, but exactly half was above, exactly half must have been below somehow. So interesting. Again, sometimes, well, yeah. Sometimes you're just cranking out double integrals and trying to get the answer. The answer is 0. Sometimes you're trying to interpret what the hell that means, you know, geometrically. That's all I got is area, volume, heights. That's what I got to try to interpret what it means. Okay, let's do another one. Let's do, okay, I'm going to do this one, 21. So I'm in 14.3. 21. I like to do homework. 21 is 0 to 3, 0 to 9 minus x squared. Okay, it's a double integral. 0 to the square root of 9 minus x squared. Wait, hang on. Is that what it said? Yeah. 21. 0 to the square root of 9 minus x squared. 0 to 3. So this is in x's and y's. It is x squared plus y squared to the 3 halves. X squared plus y squared raised to the 3 halves dy dx. So right, so this is a double integral in in rectangular coordinates, and yeah, I don't even want to think about I could start trying to think about doing it, and I would quickly decide, yeah, I can't integrate this. I can't really integrate this whole quantity to the 3 halves. I got to integrate with respect to y. Yeah, it's terrible. You know, so what's the hint that I should turn it into polar coordinates? Well, the book says, convert it to polar coordinates and do it. You know, part of the hint is that When you have an x squared plus a y squared, that's easily converted to polar coordinates. X squared plus y squared is r squared. So that's sort of part of the hint. You know that you can simplify this big time if you convert to polar coordinates. The other hint, though, really the more of the hint of why we do it in polar coordinates is the region over which we're integrating. If we're integrating over a square region, you don't do that in polar coordinates. A triangular region, you don't do that in polar coordinates. If it's a circular region, we integrate in polar coordinates. It's better. So let's talk about the region again before I do the converting. What is going on here? The way this sits, what I have is bounds for y, and my bounds for y are y equals 0, which you all know what that is. And the upper bound for y is this thing. Do you know what that is?
It's upside down parabola, shift up 9.
Not quite. With the square root on it, that would have been right without the square root. With the square root on it, it's a semicircle actually. Let me just help you and remind you. Watch. What I'm talking about here is y equals 0 is one of the bounds, and then y equals this is the other bound. And anyway, I'm real good and familiar with this. That's a semicircle of radius 3. But to convince you, watch what I'll do. Square both sides.
Y squared.
Move the x squared over. And now you might realize, oh, dude, I know what that is. That's a circle centered at the origin, radius 3. Anyway, when you solve it for y, though, you get this top half of the circle of radius 3 centered at the origin. The top half, the semicircle. So that's what that is. Semicircle, radius 3. So y is going from 0 to the semicircle. So that's cool. But wait a minute. What's x doing? X is going, from left to right, 0 to 3. That's what x is doing. 0 to 3. So starting at 0 and going to the right to 3. So it's this region. When I first did this, I overdid it. I did the whole semicircle, but it's not. It's from 0 to 3. Those x values restricted. So cool. It is a circular region, but it is just a quarter of a circle. My point is, this is the convincing, because it's circular, and mine doesn't look too circular, because it's circular, that's the real kind of reason why I want to do this in polar coordinates. It'll make these bounds a lot easier. Here we go. We're switching to polar. Now, again, one thing, there's a lot of things, but you're switching this to polar, and that is just kind of a matter of substitution. So it does become r squared to the 3 halves. Now, the truth is, I could work on that a little bit. I'll simplify that later. What about the dy dx? What does it turn into?
R d theta.
Good. R dr d theta. Thank you. It comes with that extra r. We know that. Good. We know that. It sure does. R dr d theta. Well, cool. So that's part of the converting. You convert the integrand and the dA. You convert it, and that's easy enough. But to convert the bounds, you don't really read these. What did I do? I read these, sketched the region, and now I have to rethink the region in polar coordinates. So it's all about the sketching. There's a lot of sketching, as you can tell. I got to sketch this region and rethink it as I set up these polar bounds. Okay, R is going to go first. How does R go? From the origin out, I think R goes from 0 to 3. See, the name of this guy in polar coordinates, this curve is named R equals 3. In rectangular coordinates, this is his name, right? In polar coordinates, it's R equals 3. It's beautiful. So my R goes from 0 to 3. I want you to see the inner to outer idea, though. Cool. 0 to 3. Theta. Theta's easy. What's theta?
0 to 3.
0 to what?
3.
No, theta is the angle that goes from 0 to... yeah, what do you call that? Yeah, thank you, 90. Right. But you don't call it 90, you call it, because we need it in radians, we need numbers.
Yeah. I was thinking like the x-axis.
I forgot what it was. It's been a long time.
Well, hang on. If this is 0 in radians, this is 2 pi, right?
Oh,
Right, is it-
What's halfway?
so that's pi.
That's pi.
And pi over 2.
That's half. Yeah, there's half of that. Right, pi over 2. Cool. 0 to pi over 2. So that's cool, huh? That's converting. That's converting. It's not hard, really. You got to know your little kind of your polar equations. Your how to convert x squared plus y squared is r squared. I think they want me to do this problem. I guess I could do it. But I think the converting is the more interesting part. You know, again, though, real quick, this is the square root of r squared cubed. So hang on a second. The square root of r squared will be an r. And then when you cube it, it'll be r cubed. Times this r, though, will be an r to the 4th. So this is really an r to the 4th sitting here. And I want to integrate it. I guess it's 1/5 r to the 5th. From 0 to 3, you plug in your 3. You get 81/5. No, that's not right. 3 to the 5th, yeah, I did that wrong. 3 to the 5th is 243, I think. You get 243/5. Okay, now wait a minute. That's the answer to the inner integral. There is still one more integral to do with respect to theta from 0 to pi over 2. The cool thing is there's no variables in there. There is no theta in there. So to integrate that number with respect to theta, you get that number times theta. When you plug in your bounds, you get the pi over 2 plugged in there. So we're done here. It's kind of anticlimactic at the end. When I plug the pi over 2 in there, I'm going to call it pi over 10. And that's a number, and it's a certain amount of volume. Whatever the hell this thing is, it lives up above here, and the volume above here is that number. You guys okay? Cool. This is good. Little polar coordinate problems here for a second. I might want to do I might want to flip toward the end and do a more complicated version, but maybe I'm going to step back to 14.2 a second. There's some good problems, you know. I'm going to go ahead. I'm not going to do this one. By the way, we're off Friday, so we got a long weekend. I'm going to tell you this. In 14.2, I really love number 29. So y'all ought to check it out. Maybe you'll ask me about it next week. I don't want to do it now, but I want you to try it. That's a good one. I think I did 31 the other day in that little region of problems. I didn't do 30. I did 30. So 20, there's a few assigned problems there that I like in 14.2. Right now, though, let's do this 38. So in 14.2, I want to do 38. Now this is kind of weird. They got a couple pictures there. The pictures they have in the book are for 33 and 34, and then there's this 38. They give me these two things: z equals x squared plus y squared. So by the way, just to keep in mind, I'm back in 14.2 before I learned about polar coordinates. You know what though? I may need polar coordinates for some of this. We'll see what happens. They gave me that surface and they gave me this surface. 18 minus x squared minus y squared. 18 minus x squared minus y squared. So the directions say this, which might help. The directions say, in exercises 33 through 38, set up a double integral. Oh, they don't even want me to do it. They want me to set it up. Set up a double integral to find the volume of the solid region bounded by the graphs of these equations. But the title is called The Volume of a Region Bounded by Two Surfaces. See, I think what they're giving me here is I think I got an upper surface and a lower surface. Now, that's not, I haven't been talking to you like that. I've been doing, you know, when I do this double integral, I say, there's a surface here and it lives above the region in the xy plane. But apparently now I got two surfaces. Do you have a thought on how to get the volume between two surfaces?
Take the difference between the two.
Thank you. Good idea. That's kind of an old Cal 1 idea. If you're trying to find the volume between two functions, the area between two functions, you would do top curve minus bottom curve. That was kind of a good catchphrase to get the area between two curves. Well, if we want the volume between two surfaces, let's do a double integral and we'll do the top surface minus the bottom surface. Right, the volume between two surfaces. Awesome. Okay, now I got to figure out who's who here. I know these guys. I can help you with a good picture here. This is your very basic paraboloid. He's called a paraboloid. He sits at the origin and he opens. He's actually very nice and circular. He's a nice, although in general he's called an elliptical paraboloid, but this one with the same coefficients here, this is a nice circular paraboloid here. And it goes up forever. It goes up forever. Okay, we've run into this before. Very similar to what I just said, except a few differences. With the plus 18, you might say, okay, it's pushed up 18. With the negative signs in front of that, you might say it's upside down, and you'd be right. So what you have here is this guy is an upside down paraboloid, up 18 and headed down. Also very circular, those coefficients. Now, this guy's headed up, this guy's headed down. You know, I drew this picture like they intersect. I guess they would intersect. Boy, let me get this labeled correctly here. This is my upper surface then, and then this one's my lower surface. Right, you guys? You can follow those arrows. Well then, okay, you're onto something then. You told me what to do. You said, set up a double integral, all right? Set up a double integral, and you said, top curve minus bottom curve, kind of like old Cal 1 idea. Right, top surface, 18 minus x squared minus y squared, minus, top z minus bottom z. And my bottom z was this one, x squared plus y squared. That's pretty cool. I can clean that up a little. What about bounds? Do you want to do dy dx or dx dy?
dy dx.
Okay, he wants to do dy dx. Okay, the truth is, it does not matter hardly at all in this problem. In a way, maybe you don't know why yet. You can't really make this decision until you start thinking about the region. And so I'm about to start thinking about the region. I got the integral set up, but now to decide whether it's dy dx or dx dy, I need to think about the region over which I'm integrating. To get the bounds, I need the region over which I'm integrating. So now I want to look at the 2D region over which I'm integrating. Now here's what's funny. If you take a look at this guy and look down in the xy plane, you might say, holy shit, there is no region. What am I integrating over? There is no region in the xy plane. There's just a point. Well, then what you need to realize is the region in the xy plane is the shadow of this thing in the xy plane. You said that before. We were sort of saying that last week. And so it's the shadow of this thing at its widest point. So the region over which I'm integrating is sort of right here, where they intersect each other, shadowed down. This is the region over which I'm integrating. Probably some circle where they intersect. Wow. So now I'm curious where they intersect. What would you do to think about intersecting? Two surfaces intersecting. What would you do?
Set them equal to each other.
Set them equal to each other. Thank you. That's an old phrase from 2nd grade. You're right. I'm exaggerating. But you're right. Set them equal to each other. Yeah. To think about where they might intersect. Right. The intersection of the two surfaces. That's kind of what I need. That's interesting, right? The intersection of the surfaces is what I need to form my region. The intersection of the surfaces is that widest point that forms the region over which I'm integrating. If you add these x squareds and y squareds over here, you get 2x squared plus 2y squared equals 18. If you divide by 2, you get x squared plus y squared equals 9. This must be the the region where they intersect, but the shadow of that is what I want. And what is it?
It's a circle with radius
3. It is a circle of radius 3. That's pretty cool. That's where these guys must meet. They meet at a circle of radius 3. They meet when, by the way, that must be when z is 9. Let me just check that out. When z is 9, I'm at a circle of radius 3. When z is 9, and I move a few things over, I'm at a circle of radius 3. So when z is 9, I'm this. But that shadow in the xy plane is what I'm looking at. So cool, you're right. The region over which I'm integrating is a circle of radius 3. And that's its equation. And now I'm going to kind of act stupid here for a minute. I mean, so pretending, like I am in 14.2, right? So pretending I'm in 14.2, and I haven't learned to switch to polar yet, because by the way, wouldn't you really love to switch this to polar? Yeah, it's a circular region, please switch to polar. But let's pretend we haven't learned that yet, because we haven't. And let's just remind ourselves how nasty this is going to be. Okay, watch. So if we decided we're going to let y go first, then I need the lower y and the upper y. I might say that the lower y is this bottom semicircle. And do you know its name? When you solve for y, you move the x squared over, you take the square root, and you get the negative square root of 9 minus x squared. The upper semicircle is
positive square root.
Y equals the positive square root of 9 minus x squared. I mean, that's my lower and upper semicircle. That's my lower and upper y. So as you can tell, these are kind of nasty bounds here, but these are the bounds for y. And while y is doing that, lower to upper like that, what do you think x ought to do?
Should be...
I need bounds for x. That's the last thing I need, bounds for x.
So it should be negative square root of 9 minus y squared and positive of that.
Okay, good. You're talking in general. And if you wanted x to go first, that's how you'd have to talk. But since I let y go first, he's kind of in general. And then x is the most extreme left and extreme right. You know, it's easier. It's when x goes last, it's easier bounds. What is it?
Negative 3 to 3.
Right, right. The last bounds are always numbers. Well, there you go. This will be so much fun. You know, the truth is, this problem 38, the directions actually did say, set it up. They didn't even want me to do it. I don't really blame them. I think this is horrible. Let me just see something. If you combine some like terms, this turns into 18 minus 2x squared minus 2y squared, I think. And then here I am trying to integrate with respect to y. Watch this. You ready? Let's try this. If I integrate with respect to y, I get 18y minus 2x squared y minus 2/3 y cubed. Are you guys okay?
Yeah.
Now look, what the hell am I going to plug in for those y's?
Oh, wow.
Yeah, these nasty square roots. I got my lower square root and my upper square root, and that's what I got to plug in for y. Oh my God. I got to plug that one in, then I got this negative one. All right. Right. So, what's the conclusion?
Polar.
Yeah, switch to polar, man. I swear, it's so much better. I mean, you got to struggle through a few of these maybe to feel the appreciation for the polar. And I haven't even made you struggle through it. You can imagine. You can imagine the struggle. So let's do this. I'll tell you what. Let's switch this whole thing to polar. And, you know, here he is, or in a way, here he is, a little more simplified, or there it was. But to switch to polar, this has to switch to polar. You know what to do with that? It's easy, but you kind of factor out the -2, and it leaves you with x squared plus y squared. I mean, that's what a -2x squared, -2y squared is. It's this, and now maybe you know what to do. That's r squared, right? So that's 18 minus 2r squared. Okay. What about the dy dx?
R, dr, theta.
And that r becomes part of the integrand, and it needs to be distributed times this whole integrand here. So maybe parentheses are important. That r is going to come join all that junk. Okay, cool. Now I need bounds for r. Where's my region? Where's my region? Oh, here's my region. Forget about the y's and x's. Bounds for r are so easy. Bounds for r.
It's
0, 3.
0 to 3. Bounds for theta. Theta?
0 to 2 pi.
Yes. This region in polar coordinates is, ignore these now. If I'm integrating over this region in polar coordinates, I let my r go first. R goes from the origin out, 0 to 3. While r does that, theta goes from 0 to 2 pi. It's so beautiful and easy. All right, that was fun. You know what? I'm not going to bother finishing that one. But now it's easy now. You distribute the r and you integrate with respect to r. And I think you'll get a number. At the end, you'll get a number, and you'll integrate that number with respect to theta. You'll just throw a theta on it, put a 2. Right. Okay. Let me see. Is there anything else here in 14.2? I think I told you a little bit about an average value. I did do that. There's a 58. It's kind of an average value question. There's a 68 that I asked you to look at and think about. It's kind of a think about it problem. I won't talk about those. I want to let you think about them. So I'm going to move back to 14.3, and I'm going to get to a little tougher 14.3 problem here. Okay. All right, number 38. Okay, again, another number 38. I'm up in 14.3 though now. Moving up to 14.3, number 38. The question says, find the volume of the solid, and then they say this, inside the hemisphere. So it's nice of them to use some words and tell me what's going on. The hemisphere is z equals 16 minus x squared minus y squared. So they're saying inside the hemisphere, and then they say, oh wait, what did they say? Let me read this. Inside the hemisphere and outside the cylinder. Outside the cylinder, x squared plus y squared equals 1. So again, I think, what might be the hard part of chapter 14, who knows, there's a lot of little hard parts, integrating, whatever, but it's the visualizing and the drawing and the sketching of these 3D things. Now they were nice enough to tell me it's a hemisphere. Could you tell me the radius of that hemisphere?
4.
What'd you say?
Is it 4?
It's 4, yep, good. So that's a hemisphere. And one more time, to convince you it's a hemisphere, what do I do to convince you? I mean, they told you. But if I needed to convince you it's a hemisphere, I would square both sides. And then you'd get z squared equals 16 minus x squared minus y squared. You'd move these two dudes to the other side, and you'd get x squared plus y squared plus z squared equals 16, and then you know what the hell you're dealing with, right? I mean, you're more familiar with this. But by now, you might be getting familiar with this. I mean, when you solve this for z, this is how it plays out, right? So it's a hemisphere, radius 4, right? Also, this is a cylinder, radius 1. I mean, when you look at that, you might say the word circle, radius 1. And it is a circle in the xy plane, radius 1. But if the z-axis is coming out and there's no z, with a missing z variable, this runs parallel to the z-axis. It's a cylinder coming out at you if the z-axis is coming out at you. So okay, so let me draw a 3D picture of this if I can. Then we're saying, what are we saying? We're saying there's a hemisphere of radius 4. That's not bad, is it? All right, that's a hemisphere of radius 4. And then inside there, there's a cylinder of radius 1. If I color coordinate this, it might look better. So there's a cylinder of radius 1 that goes, I mean, it goes infinite. You know, this cylinder has a nice spherical top, I guess. Kind of hits it has this nice spherical top on this cylinder. But what is the volume they wanted? They wanted the volume inside the hemisphere, but outside the cylinder. So not in that cylinder, but actually they wanted all this volume out here. Whew. All right, maybe I can do that. Here I go. I think I'll set up a double integral. What I need is to organize my brain. Again, I keep doing this to you. Hopefully you're picking up on this. I don't need to worry about the region right now. What I need to worry about is who am I integrating? Who is my ceiling? Who am I integrating? Who's my Z? Who's my top? Who's my ceiling? And what is it?
It's the dome minus.
It's the hemisphere, right. That's who I'm integrating. I'm integrating that surface. I mean, that's the top, and that's this guy. So that's what I'm integrating. I'm integrating that surface. Okay, and then I can think about dy dx or dx dy. Hang on. But now I should look at the region over which I'm integrating. So I did all this 3D work just to help get a feel for really just who's on top and what am I doing. But now I need a 2D picture of the region. I think a 2D picture of the region is this region, which is a circle of radius 4. But wait a minute. What I'm not integrating over is that I'm not doing this, right, you guys? So that means there's a circle of radius 1 that I'm not doing. So the region is this. You're with me on that, right? That's the region over which I'm integrating. And it's circular, it's very circular. That I should switch to polar. So I started to set this baby up, and I'm going to abandon him and switch to polar. It doesn't take too much. What does this turn into when you switch to polar? You factor the negative sign out.
Right, so it's 16 minus r squared.
That's what it is. That's what it is. It's 16 minus r squared. Yep, it's easy. All right, cool. It's 16 minus r squared. And what do I put out here?
r
d theta. Cool, cool. See, so that's, I don't know. See, I've got, my brain, my problem solving technique is I break things into little chunks. So I worked on this part. Whew, that was easy. Now I got to work on the bounds. That's a different chunk. But there's the region, and I hope maybe I can see the bounds for r and for theta. I mean, let's just skip to theta for a second. What's theta going to do?
0 to 2 pi.
0 to 2 pi, thank you. What about r? It goes from the origin out. We don't want this stuff. When we hit the 1, now we want stuff. From 1 to, I would say it's from 1 to 4. That's my r, going from, instead of going from 0 to 4, I don't want 0 to 1, so I'm going to go from 1 to 4. From 1 to 4 for r, 0 to 2 pi for theta, and it probably isn't that hard. I mean, every integral presents its own integration challenges. This one we did the other day, we did a u substitution on this. It helps kill this r. I mean, I could help you finish this one, or I could just let you do that. I mean, let's pause a second. Are you happy with the setup? You guys are all convinced? Cool. I'm integrating this ceiling. I'm integrating over this region, which I drew better, so I could think about this region, and I set up the bounds for this region. There it is. You know, on a test, I've had students do this. A problem like this shows up on a test, and they go, They set up from 0 to 4, 0 to 2 pi. They got this all set up. And then they go minus from 0 to 1, 0 to 2 pi. In other words, they do it all from 0 to 4, and then they realize they don't want the 0 to 1, so they subtract it away. It's like they find all the volume and then subtract off this volume. I mean, that's fine, but it's a little overkill. You don't have to, you can do it like this. Right? You don't have to, maybe I don't realize you can do it like that, but you can. You can do it like that. Yeah, okay. Well, there's a few good ones like that. So 14.3 gets good kind of up in the, there's a nice batch of, I think I assigned 33 through 40 or 35 through 40, or there's a nice batch of little more challenging problems like this. I mean, I think they're challenging, but I don't know. It wasn't much more different than any of my other problems, really. But there's some good ones there. So I don't think I'll finish this one. And I think I'm about done today. It's almost time to leave, but let me tell you one thing. I think we're going to skip 14.4 and 14.5. I may just talk about some stuff that's in there. I may tell you something. But the next stop really kind of is 14.4 and 14.5 are more uses of double integrals. Besides volume, you can do some centers of mass. You can do some moments of inertia. But you're using, I mean, those are kind of physics ideas that you're using double integrals to do. Surface area, you can do surface area. So I'm kind of stuck with this volume idea, and I tend not to go do all those ideas. We might do something, But then after that, those two sections of more double integrals end, and when you get to 14.6, it's a triple integrals. So if it's a triple integral, it's a triple integral. And guess what? You're probably doing, what we call a dV instead of a dA. And I don't say I'm integrating over a region. Now I'm integrating over what we call S, a solid. S is a solid. So I'm integrating over a 3D solid instead of integrating over a 2D region. And I'm integrating with respect to the volume of that solid rather than with respect to the area of the region. That was the language. The dA was integrating with respect to the area of the region over which we're integrating. This is integrating with respect to the volume of the solid we're in. But anyway, guess what the dV turns into? You can kind of imagine. dz, dy, dx. So your first integral would be for the z's, your first bound would be for the z's, your next one would be y's and x's. You'd have to work on that. But yes, here's the problem. If you wanted to do it in another order, it's not a problem, but it is a problem. If you wanted to do it in another order, there's 5 more orders. You could do dz, dx, dy. You could do dy, dx, dz. You could do dy, dz, dx. You could do dx, dy, dz. Or you could do dx, dz, dy. I think I just organized there's 6 different dv's. Makes you long back for the dA, which is only dx, dy, or dy, dx, or r theta. But anyway, so there's 6 possible orders of integration, and then they kind of make you mess around and do that, which is kind of tricky. Let me just finish one thought here. This is a little introduction to 14.6. I'm really not going to do anything, but if you remember the way this chapter started, I did a double integral over the region R, dA, and when there's no function there, just a 1 there, it was really the volume of something with a height of 1, but we called it area. The book called it area when there's only a 1 there, so we called this the area of region R. All right, so then we said, well, when you put a function in there, then this is the volume between the function and the region R, and then we called it volume. But again, that was kind of a lie. This was really volume 2. All right, so now I'm in triple integral, and the analogy kind of continues. So a triple integral over a solid S with dV, with without a function there, just a 1 there. So now this is volume, and it's the volume of the solid S. Kind of like this is the area of the region R. This is the volume of the solid S. But I guess maybe that's kind of a lie. It's really the... See, now here's the problem. There's no fourth dimension analogy to volume, so I don't know, I don't have a word, but there's... Right. This was really volume of something with a height of 1, but we call it area. This is really the fourth dimensional volume of something with a height of 1. Height ain't even the right word. I mean, I lose words here, but so this is the volume of the solid S. And what if you did a triple integral that had a function in it? So now you're really up another dimension. I mean, now this is some fourth dimensional quantity. I don't have a geometrical idea for this. Now, there's a lot of physics ideas here. If this is a density function and you're integrating the density over a volume, perhaps you're calculating the total mass. I mean, there's some physics ideas where this makes sense. But if I'm just trying to stick with my area, volume, geometry idea, then I lose it right here. I totally lose it. I don't have anything to say except only God knows what this is. No, I'm sort of kidding. But my point is I lose my geometry, and like I said, there's some physics meanings for this stuff. If that function means, like I said, density, and I'm integrating over a volume, perhaps I'm calculating some physical quantity like the mass of that object or something. So just a quick story about what's coming up with these triple integrals in 14.6. But we're going to do them kind of quick, and then we finish with some triple integrals in some new coordinate systems. Just to let you know where I'm headed next. So we'll go do a little 14.6. But then I got to jump back to 11.7, and I got to learn some new coordinate systems that I skipped at the time, because I need them to help me with 14.7. So there's these two come next after this learning about these triple integrals. And then we're kind of done with the chapter, but this is some good challenging stuff up here. So anyway, got a long weekend. Next Monday, maybe I'll do a little of this and get into a little of this next Monday. We'll see. But we'll quit today.